Hello my dear students, good evening to you all. Myself Vipin Mishra, the lead mentor at IMS GATE Academy. I hope that you all are preparing well for the GATE exam, and in the meanwhile you are also enjoying the GATE Score Booster series of IMS GATE Academy. Now in this series I have taken 2 sessions on power electronics, and you people were there and you have enjoyed those sessions. There we discussed some fantastic questions along with the formulas used, and we also discuss how we can approach for those formulas. Okay. Now today I will be taking one session on power system, and tomorrow also we will continue with power system. So again, here also I have designed some fantastic questions that are the probable questions for the upcoming GATE 2024 exam. So let's get started with power system. So if I talk about power system, these are the important topics or chapters that we have to cover. So the first one is the compensation technique, second one is the load flow analysis, third one is insulators, cable and distribution, fourth one is fault analysis, and then the fifth one is power system stability, followed by performance parameters of line, and last but not the least, power system protection. So these are the topics that we have to cover in this particular power system chapter, and it is a very important chapter. It is a very important subject, by the way. It has a weightage of around 11 to 13 marks. So if you are very well prepared for power system and power electronics, you are going to score good number of marks, and definitely you will be getting a good rank as well. Now these GATE Score Booster sessions will really help you. Not only power system and power electronics, right now the sessions are being conducted on several other subjects as well. So you can just go into our playlist and you can follow all other subjects as well. In this way, you can be very well prepared for all the subjects and ultimately for the GATE exam as well. This will give you a good amount of practice. This will also give you the taste of some unseen questions, so that you can prepare yourself very well for the GATE exam. Okay. So first chapter that we are going to discuss here is the compensation technique. Now if I talk about the compensation techniques, what are the important topics that we should cover in this particular chapter? So the important topics in compensation techniques are power flow through transmission line, methods of reactive power control, traveling waves, and load frequency control. Out of these three are very important topic. Okay, regularly they are giving GATE questions. Traveling waves also an important topic. Okay, sometimes you may see a GATE question from this chapter as well, this topic as well, but questions are not frequently coming from this chapter, but other three topics are very important. Okay, so traveling wave and other three topics are very important. So let's get started with the very first question of this session. So here it is. This is the first question that I have from compensation techniques, and what has been said in this question is, the single line diagram of a power system is shown below. Generators G1 and G2 are connected through a transmission line of impedance J.4 per unit. So we have two generators connected together with a transmission line of impedance J.4. Given load at G1 and G2 are S1 equals to 8 plus J10. So value of S1 is 8 plus J10. This is the power rating. And the value of S2 that we have is around 5 plus J12 per unit. Voltages V1 is 1 angle 45 and V2 is 1 angle 0. So here we have the voltage 1 angle 45 degree, and here we have the voltage 1 angle 0. So this is the given data. If power factor of G2 is unity, so G2 has a power factor of unity. Okay, G2 is operating at the unity power factor load, then reactive power supplied by the capacitor will be what? So this is the capacitor installed here. What reactive power it is supplying? QC, let me call this QC. So this is what we have to calculate here. Okay, I hope you understand the question. So these are the two generators connected through a transmission line of impedance J.4. The power supplied by S1, G1 is given S1, power supplied by G2 is given S2, and G2 is also operating at unity power factor. There is a capacitor installed at G2 at this bus. Okay, so what power, what reactive power capacitor is providing for the compensation, this is what you have to calculate. Mean you have to calculate what could be the possible value of QC. This is what we have to do here. So I hope you understood the question. Now let me give you time. So I am giving you a time of 2 minutes for this question. I hope that you will be able to solve it. And your time starts now. Did you understand the question? Just reply if you understood the question, what has been said and what you have to calculate. Reply in the chat box if you have understood the question, what has been said in this and what you have to calculate. So we have last, the time is already over. Is there anybody who got the answer for this question? Tell me guys, is there anybody who has solved this particular question and got the answer? Okay. So just see what has been given to us and how we can solve these type of questions. Okay. So if you see, the S2 has been given to us, and what is the value of S2 given to us? 5 plus J2 per unit, 5 plus J12 per unit. Okay. What will be the possible value of QC? That is what we have to calculate here, and generator G2 is operating at unity power factor. So if it is operating at unity power factor, the contribution of generator G2 will be 0. Okay. And then contribution to generator G2 will be 0. And how much power we are getting from here? How much power is being transmitted in the line? Let me call that QT. Okay, so QT is the power which is transmitted to the line, and how much is the value of QS2 supplied to the load. Okay, so just see the power flow. Now, good evening Thiru. Now if you see, if we just apply, just see the power flow here. So incoming powers are QT and QG2 and QC, and outgoing power is QS2, isn't it? This is what we will get here. Now what are the values of different powers? QT, do you know the value of QT? No, we don't know. So how do we calculate QT? QT is the power transferred from generator 1 and to generator G2N. Okay, so this is the transmitted power. So we can calculate this transmitted power, and how we can do that? So transmitted power QT, if you have to calculate this, we have a formula for this. It is equals to Vs VR upon X cos del minus VR square upon X. Okay. Now by using this formula and putting the values, What is the value of Vs? Vs means sending end voltage. So this is the sending end voltage. What are the values of voltages we have? It is 1 angle 45 and this is 1 angle 0. Okay. So Vs and Vr both are equal to 1. The value of x is 0.4. Cos of del is the angle difference between V1 and V2, which is 45 here, minus Vr, which is 1, divided by 0.4. Now when you will put the values and when you will solve it, you will get around minus 0.73 per unit of power. This will be the QT value, means the transmitted power from one end to other end. Now if we will come back in this equation and we will put the values. So here what we have? Minus 0.73. What is QG2? This is 0 because it is operating on unity power factor. Then what is the QC is what we have to calculate, and what is QS2? Supplied to load S2. So the reactive power supplied to load S2 is 12. Now from here what will be QC? So QC will be 12 plus 0.73. So what we will get? 12.73 per unit, and that will be the answer. So see, this is how you could have solved this question very easily. Okay. It seems to be a very tough one. It seems to be a very difficult one, but the logic is very simple. You just have to see the power flow across this particular node, isn't it? Because what we have to calculate? We have to calculate QC. So how is the power flow across this node? Just see here. So QC will send some power, okay, or it may take power as well. If suppose the sign of power is coming negative here, and in that case capacitor might be taking the power. So we assume that it is supplying the power. Then we have S2 which is taking the power. Then we have generator G2. So how much is the contribution of generator G2? The power factor is 1. So the contribution of generator G2 will be 1. It will be supplying only active power. No reactive power requirements are there. And then what is the power transferred from generator 1 end to generator 2 end? Let me call that QT. And we can calculate the power transferred through this formula. So this is a very important formula for you all. Okay. So through this formula we calculated what is the value of QT. Then when we applied the power flow here, it was very easy for us to calculate QC. And how much is QC? 12.73 per unit. Okay, so this is how we can solve this particular question. I hope you all understood this question and how to approach for these kind of questions. The purpose of this series is to make you aware of what kind of question you can get in the upcoming exam and how you can approach for them. If you have some unseen questions, how you can apply the concepts that you have studied in the class, and how can you correlate the question with the concepts and the approach to solve a particular question. So this is the purpose of this series. So just see how easily we have solved this particular question, which seems to be a very difficult one, but we have managed to solve this question. Now you can expect this kind of question in the upcoming GATE exam. This is a very good question. Okay, I hope everybody understood this. Now moving towards the next question. So just see this particular question. What has been given here? Let me just read out this particular question. So a power station is shown in the figure below. So this is the power system. The station is connected with load through a 440 kV double circuit transmission line. So this is the generator and this is the transformer. Then we have double circuit transmission line, and at the end we have another transformer. Then finally we have the load. Double circuit transmission line of length of 200 km. If the initial real power transferred is 0.72 per unit at 0.8 power factor lagging. So the power transferred is 0.72 per unit. Okay, and it is being transferred at the power factor of 0.8 lagging. Okay, at the load bus voltage of 1 per unit. Okay, so the load bus voltage is 1 per unit. The load bus voltage is 1 per unit. So V is given to us 1 per unit. Then maximum power transfer will be. So how much is the maximum power transferred from this generator to the load in this particular situation when we are supplying a load of 0.72 per unit at a power factor of 0.8 at a voltage of 1 per unit will be what? This is what we have to calculate here. Okay, and I hope that you people can solve this question. So let me give you time, and I know that you people can solve this question. So your time starts now. Take your time and give me the correct answer. Read it carefully, and I know that you people can manage to solve this question. You have to calculate the maximum power transfer from generator to the load, okay, under these conditions. So we are left with last 30 seconds. Okay, take your time. In GATE we have almost 3 minutes for each question. Okay, so you can spend time on this question, and it is doable. So I want a correct answer. So anybody who has solved this question? Okay, so just see, we have to calculate maximum power transferred, which is equals to EV upon X equivalent. Okay, now do you have the value of E given to you? No. Do we have the value of X equivalent? No. So these two things are unknown. If we can manage to calculate these two, we will be able to solve this question very easily, isn't it, with the given data? Okay, so just see what we can do with the given data. So from this given data, you can calculate the current. So current will be simply P upon V cos phi. This is why they have given you this particular data. So it is 0.72 divided by 1 into 0.8. So what you will get? You will get 0.9. Okay. And what will be the power factor of current? It will be minus of cos inverse 0.8 because the load is lagging. So what you will get? This is the value of current. Okay. So finally you will get 0.9. The angle will be minus 53.13 degree. Okay. Are you getting the same value of current and power factor? It will be 36.86. Okay. It will be 36.86 degree. So you have calculated the value of current, okay, with the given data. So now the current value is with us. So how much current is flowing in the circuit? The current flowing in the circuit is 0.9 and the angle is minus 36.86 degree. This is the value of current. Okay. We want to calculate the value of, what do we want to calculate? We want to calculate P max, and the P max is E into V upon X equivalent. So we want the value of X equivalent, we want the value of E. How to calculate X equivalent? Okay. So just see, from this particular circuit which is given to us, if we just draw the diagram. So just see what is given to us. Generator is having some reactance, and what is that reactance? It is 0.5. Okay. Then we have transformer, and the transformer is having a reactance of 0.2. After that we have a double circuit line, and this double circuit line is having a reactance of 0.6 each. Okay, this is 0.6, this is also 0.6. After that we again have a transformer which is having a reactance of 0.2. 2 per unit. Okay, and then finally we have the load. So what will be the X equivalent here? So X equivalent will be 0.5 plus this 0.2 plus the parallel combination of 0.6 with 0.6 plus 0.2. Okay, so how much you will get? 5 to 7, and here you will get 3 and then 0.2. So you will get 1.2 per unit. This will be your X equivalent. Okay, so now the two things are known to us. We have calculated the value of I, we have calculated the value of X equivalent. It will be J 1.2 per unit. Okay, now we have with us these two data. So we have to calculate now. Only unknown thing is E. So we have to calculate E now. Okay, so if we apply KVL, E will be simply V plus J X equivalent into the current. Okay, so V is basically 1 angle 0 plus what is X equivalent? 1.2, and what is the value of current? 0.9, angle is minus 36.86 degree. Okay, so we have all the data, we have written all the data. Now when you will solve it for E, what value you will be getting? So when you will solve it for E, you will get 1.85, you will get 1.85, and the angle will be 26.67 degree. Okay, so this will be the value of E that you will be getting. Now from here again we have calculated the value of E. Now what will be the value of E? It will be 1.85 per unit. So now we have all the values with us. So what will be the maximum power transferred? It will be E into V upon X equivalent. So what is E? 1.85. What is V? 1. And what will be the value of X equivalent? So X equivalent will be 1.2. Okay, now when you will solve it, you will be getting an answer of 1.54 per unit. 1.54 per unit will be the answer. Is that an option given to us? Yes, option number D, 1.54 per unit. So this is how you have to approach for these kind of questions, and be ready. These questions are very important. Okay, you may be doing this exercise, maybe a question mixed with some power system stability concept may be asked in the exam, where you have to do this exercise, because there we require the value of P max as well. So be prepared. A question may come with a mixed concept of power system stability as well, where you have to do this minimum exercise. Okay, so how to find the value of E, then how to find the current, then how to find X equivalent, and finally calculate P max. So this question has a lot of things, okay, that you can learn from this question, and that's why it is an important question. Okay, so this is how we can manage this question. I hope this is clear to everyone. So now we can move towards the next question. So just see, this is the next question that we have. So let me read it out. A transmission line has impedance of 3 plus J4 ohm per phase. Fine, it has an impedance of 3 plus J4 ohm per phase. Let me read right here, 3 plus J4 ohms per phase. Okay, if we write it into the polar coordinates, it will be like 5 angle 53.13 degree ohms per phase in rectangular coordinates. Okay, this is Z, and you know that impedance is written like B angle beta. Okay, so you got the value of B, which is 5, you got the value of beta, which will be 53.13 degree. Okay, I hope you also getting the same answer. When you will convert this impedance, you will get this value. Okay, now with a load of 10 megawatt, 0.8 leading power factor. So what are the values of load that we have? Load is having P of 10 megawatt. And what is the load power factor? The load power factor is around 0.6 and it is leading. Okay, so P and power factor is known to us. If we want to calculate Q, how you can calculate Q? So P tan phi is Q. Okay, and for phi you will calculate cos inverse 0.6. Okay, and in place of P, what we can write further? 10 which is given to us 10 10 in 10 10, okay, cos inverse 0.6. Okay, so when you will be doing this, you will be getting an answer of minus 7.5 MVAR. Okay, so why we have put this minus? Because of the load is of leading nature. So instead of consuming, it will be supplying the reactive power, and that's why we took a negative sign there. I hope this is clear to everyone. Okay, now from the given data we have calculated all these values, the value of load angle del and the compensation required. So we have to calculate what will be the value of del, and if suppose we will use some compensation. Okay, I don't know whether it is inductive or capacitive. So if we use a compensation, then what will be the value of Q compensated? Okay, so we have to calculate these two things. How much will be the value of Q compensated, and how much will be the value of the load angle del? Okay. Oh, it is 0.8. Okay, sorry. So this is 0.8. Okay. So now when you are putting 0.8, how much answer you are getting? I think it is the same. I did a mistake and put 0.6, but the data that I am having is same. So Divya, are you getting still minus 7.5 MVAR? The power factor is 0.8, not 0.6. Okay. So we have to calculate the value of the load angle. Okay, means we have to calculate this del value. Then we have to calculate how much compensation is required. So I just made a black box here because I don't know whether it is inductive or capacitive. That we will comment later. Okay, and that may also be the part of question. So this is the given data, and this is what you have to calculate. And your time starts now. I hope you understood the question. And let me give you 3 minutes because there are a lot of calculations here. Okay, Divya, are you getting minus 7.5 MVAR when you are taking power factor to be 0.8? I think the answer will be same, but I think I put a wrong value here. So take your time, and I believe that you can solve this question. Okay, we have to calculate the value of del and how much compensation we are providing. Very good. So we have last 1 minute. Take your time. Still you have 1 minute, and I hope that you can solve this question. It involves a lot of calculation, and this is a very good choice for an MSQ kind of questions. Okay. So they may ask for value of del, they may ask for what kind of compensation required, and they may also add one line in this question, what type of compensation, inductive or capacitive. Okay. So this is a good choice for an MSQ kind of question. So be ready for this question. Last 30 seconds, and I am still waiting for your answer. So what you can do, you can make a correction here. Okay, here you can write 10 megawatt and 0.8 leading. Okay, I think two datas are given, so you just go with this data, 10 megawatt 0.8 leading. Okay, so just correct it, 10 megawatt 0.8 leading. So this is what you have to take. Okay, any answer? Thiru, Divya, Nilmesh? Okay, so just see guys, what do we have? We have power given to us. Okay, the load which is consuming power, and that power consumed by the load is how much? It is 10 megawatt. Okay, let me write here 10. So this is 10 and this is 0.8. So you know that the power received by the load, we have a formula for that. So what is the formula of power received by the load? It is Vs into Vr over B. Okay, then we have cos, and I think it is also 3 plus J4 here. Okay, this is 3 plus J4 here. So I think figure values are different from the question. So you can take the values given in the question only. Okay, so Vs Vr upon B cos beta minus del minus A Vr square upon B cos beta minus alpha. Okay, now this value is given to us, which is 10 megawatt. Okay, PR, what you have to take? PR you can take 10 megawatt. Okay, so PR value is 10 megawatt, and what is Vs and Vr? We are maintaining Vs and Vr equal to 33 kV. Okay, so both will be 33 into 33, so kV will be converted into megawatt. That's why I am not writing the units. Okay, so it will be 33 square upon B. So what is the value of B? B value will be 5. Okay, then cos of beta, beta is 53.13, and we don't know the value of del. Then what is the value of A? A value, you know that normally will be chosen as 1. So A is basically A angle alpha, and we can take it 1 angle 0. So we will put the value of A, which is 1. Okay, and then finally the value of beta 53.13 minus alpha will be 0. So if you see, the only unknown thing here is, so earlier today there is a schedule of hydrology subject by Sandeep sir, but now it's not there in the schedule. That's because Nikhil, Sandeep sir is feeling unwell today. He is not feeling well today, so he will be taking the session on any other day. Okay, I hope you will get the information on the channel. So just see, only unknown thing here is del. So del value, when you will calculate from here, you will get 2.93 degrees. Are you getting the same answer, Divya, with this data? The del value coming will be 2.93. Okay, now since we got the value of del right now, so we have two information. We have the value of P, which is 10 megawatt, and we have calculated the value of Q, which is minus 7.5 MVAR. Okay, so these two datas are with us. First we have applied with P, now we are going to apply with Q. So if we apply the same formula with Q, so what will be Q? Vs Vr over B, it will be sine beta minus del minus A Vr square upon B sine of beta minus alpha. Okay, same formula, but sine will be there instead of cos. So now what is the value of Q? What is the value of Q? This Q is basically the Q transmitted over the line. Okay, so let us calculate how much Q is transmitted in the line. So if we now put the value, so Vs and Vr both are at 33 divided by 5 sine of beta, which is 53.13 minus del. Now we have the value of del 2.93 minus A will be 1, 33 square upon 5 sine of beta minus alpha means sine of 53.13 because alpha is 0. Okay, so now when you will put the value and solve it, the value of Q that you will be getting is minus 8.71 MVAR. Okay, so that will be the value of Q transmitted into the line. Okay, this is the value of Q transmitted. Now guys, we are using a compensating element here. Okay, we are using a compensating element here, QC. Okay, so what will be the value of QC? What will be the value of QC here? This is what we have to calculate. Now we have two powers. Just see the Q load. If I call this Q load, so it is minus 7.5 MVAR. So it is flowing in this direction. Okay, so if we call this power to be QR, so QR will be basically what? QR will be basically the difference of what is the load requirement, okay, minus what is transferred from the generating end to the load. Okay, so just see what is Q load. It is minus 7.5 minus what is Q transferred. The Q transferred is minus 8.71. Okay, so when you will solve it, how much you are going to get? How much you will be getting after solving this equation? I think 1.21 MVAR. So you will get 1.21 MVAR. Now this will be your QC as well. Okay, this will be your QC as well. So just see, QC will be how much? 1.21 MVAR, and since this is coming positive, so if it is positive, that means what? What kind of compensation we will be needed here? What kind of compensation we will be needed here? So just see, the difference of load requirement and the transferred power in the reactive in the transmission line or the supplied by source is coming positive. That means the requirement of load is less and supplied by the source will be more. Is it so? Or the load power requirement is less, and more is being supplied by the source. What kind of situation we are having here? I am asking you. So if Q load minus QT, Q load is the requirement of the load, okay, and QT is supplied by the source. So if we are getting this difference as positive, that means what will happen? Okay, that means what will happen? Can you tell me what will happen here? And if this is coming positive, that means we need a capacitive type of compensation here. Okay, so we will simply connect a capacitor here, and this capacitor will supply this amount of QC, 1.21 MVAR. Okay, so just see, load is giving 7.5 MVAR to this point, and source is supplying how much? 8.75 MVAR. Okay, so Q's capacitor, it will be supplying how much? 1.21 MVAR. So this is how you can calculate what values of power will be supplied by this compensating element. So just see, we have to calculate the value of load angle, which is 2.93, and we have to calculate how much compensation is required. So this we have calculated as 1.2 MVAR. Okay, so this is how we have to deal with this question. I hope this is clear to everyone. Okay, is that clear to everyone? Just cross check once again. Okay, the process is very important. You need to understand the process, how we are solving this question. Okay, and you can verify your answer later on. I hope you got it, how to solve this question. Very good. Okay, so moving towards the next question. So just see this question. This is also very important question. Okay, so what has been said here is 5 identical generators supply power in a system having lossless transmission lines. Generator 1 is equipped with a speed governor that maintains its speed constant. Okay, so generator 1 is maintaining a constant speed, whereas generator 2 and 3 have governors with droop of 2% and 3%, and generator 4 and 5 have generators with droop of 4% and 6% respectively. For a given increase in system load at steady state, option E says all generators will share the increased load equally. Option B says generator 1, 2, 3, 5 will share the increased load in the sequence of that 1 will share first, then 2, then 3, then 4, then 5, or option C says generator 1, 2, 3, 5 will share the load like this. 5 will be loaded first, then 4th, then 3rd, then 2 and then 1. And option D says generator 5 will share the entire load and the output of other generators remains unchanged. You have to choose among these options that which one will be the correct option. Okay, and your time starts now. Generators are having different groups. Okay, and if there is an increase in load, how this load will be shared, this is what you have to comment here. Divya, you understood the last question? Any problem in the last question? You can just re-verify your answer. Okay. You can just re-verify your answer and just see why I am saying that if this is positive, then we need capacitor. So just see, we are calculating the difference of load requirement to the supplied by the source. Okay. So if load required more power and supplied power through the source is less, okay, in that case what will happen? We will be having excessive power, we will be having positive power at this end, isn't it? If QR is positive, that means load requirement is more, but the source is not able to supply that much. Okay, so if load is consuming more reactive power and source is not able to supply that much power, we need to supply this externally. And who is supplying this power? Capacitor. If suppose this QR is coming negative, means load requirement is less, but the source is supplying more. In that case, we have excessive power at this terminal, isn't it? QR will be coming negative. So if you have excessive power, then we will install inductor. So inductor will take that excessive power into it. It will absorb that excessive power. Okay. So if this QR difference is positive, you have to install capacitor. If this QR difference is negative, you have to install inductor here. Okay. So this simple logic you can apply. The difference of Q load minus Q transmitted. Load means the power requirement of the load. QT means transferred from the source. Okay. So if load require more power and transferred power is not that much enough that can supply this power, that means you need external source to supply the power to load, and that external source will be capacitor. In other case, if this Q load is less and supplied power will be more, in that case load requirement you have fulfilled, but still you have excessive power at this node. So if you have excessive power at this node, you will install an inductor to catch this power out, isn't it? Because inductors normally absorb the power, capacitors supply the reactive power, you know that. So this is how, by doing this simple hack, you can solve this question. Okay, and it may be asked in that way also, that you need to calculate these two values. Apart from that, they will ask what type of compensation is required. Then if you are not doing this analysis, it will become very difficult for you to judge, and by doing this analysis it becomes very easy. Okay, so this is a trick. This trick you can apply to simply calculate what type of compensation is required. Okay. Okay, so now you can again rethink about this particular question. Okay. We have 5 generators with different droop. Now if there is an increase of load, so what will be the order in which the generators will be sharing the load? This is what you have to calculate. Okay, different generators are there with different droop characteristic. If there will be an increase in load, in what order the generators will share this increased load? This is what you have to calculate. Okay, and you have been given with the 4 options. I hope this question is visible. Okay. Last 10 seconds. So the time is over. Okay. Any answer from you guys? If different generators with different groups are there, in which sequence they will share an increased load? Okay, this is what we have to calculate here. So let me just draw a curve. So if this is P in megawatt, okay, and if this is the frequency, so just see, we have generators with different groups and we have 5 generators. Okay, this is generator G1. It is having 0% droop. Why 0% droop? Because it is written that generator 1 is equipped with a speed governor that maintains its speed constant. So there is no drop in the frequency, there will not be any droop. Then we have generator G2, generator G3, generator G4 and finally generator G5. And what are the droops? 2, 3, 4 and 5, 6%. So it is having 2%, it is having how much? 2%, 3%, 4 and 6, 3%, and then it is having 4%, and then finally it is having 6%. Okay. So if there is an increased load demand, so in what order they will share the load? Okay. So if suppose there is an increased demand, so what will happen? Just see, if I just draw this line, so just see, if I draw this line, then you can see generator 5 is sharing this load, generator 4 is sharing this load, okay, P5, P4, and then you can see generator G3, this is sharing this load, P3, and generator, this is 5, this is 4 and this is 3 and this will be P2, okay. So just see, and there is no relation with G1, isn't it? So power shared by generator G1, PG1 will be greater than PG2 is greater than PG3 is greater than PG4 is greater than PG5 as per the droop characteristic, isn't it? So who is sharing more load here? Of course, first the P1 will share, okay, and first P1 will share all the loads, then the load is distributed to 2, then the load will be distributed to 3, 4 and at the end it will be distributed to 5. So who will be having the first preference? Generator 1, because if it is sharing that increased load, there will not be any drop in its frequency, isn't it? If generator G2 is sharing some increased load, you can see there will be a drop in frequency. If generator G3 will be sharing some load, you can see there will be more drop in its frequency. Okay, if generator 5 it will be sharing some load, then there will be a drop in its frequency. So as per the droops, if other generators will share some load, okay, so as per their droop characteristic, they will share this increased load on the cause of drop in frequency, which is not at all accepted. Okay, so what we will do, we will try to avoid this situation. So first we will load generator G1, which is having 0% droop, so that it can share the max load without a drop in frequency. Then if suppose there is a necessity, we will load generator G2, then we can load generator G3, G4 and G5. So the generator which is having the lowest droop, they will be sharing the maximum load first, and then the load will be allocated to other generator with lowest droop. I hope this is clear to you. Okay. Now looking into this scenario, which option will be correct? Option number B. That means generator 1, 2, 3, 4 will share the increased load in this preference, because generator 1 it is having 0% droop, generator 2 is having 2%, 3 is having 3%, 4 is having 4% and 5 is having 6% droop, and generator with lowest droop will share the maximum load, isn't it? Generator with lowest droop will share the maximum load. Thus remember this line, okay, and whenever you are getting these kind of question, you only have to recall this fact: generator with lowest droop will share the max load. Let me write it here, okay. So the important note point is generator with lowest droop will share the maximum load. Okay, so load sharing will be in the order of lowest droop to highest droop, isn't it? So this is why option number B is a correct answer. Okay, so this is a very good question. Now this question may be twisted and you can see the question of same flavor in the upcoming GATE exam. Is that clear to you all? Divya, Nilmesh, Nikhil, and Thiru, is that clear to everyone? Okay, so if it is clear, then we can move towards the next question. So this is the next question that we have. See here, a 100 MVA alternator operated at full load on 50 Hz. The inertia constant H is 4 megawatt seconds per MVA. Time delay is 0.5 second. One of the transmission line is stripped so that the output of the generator is reduced by 70 megawatt. Okay, so earlier it is operating at 100 MVA. We can assume that the power factor is close to 1, so 100 megawatt. Okay, now from that 100 megawatt the power is reduced by 70 megawatt. So what is the remaining power that you have to see? The frequency deviation during this time will be what? What will be the frequency deviation during this time? This is what you have to calculate. So I hope this is a very easy question. Okay, and you people can solve this. If you know the formula, you can solve it very easily. To make it very clear to you, let me write here reduced to 70 megawatt. I think that will be the correct word here. Okay, it is reduced to 70 megawatt. So from 100 we have reached to 70 megawatt. Okay, now I think it becomes very easy for you. If you know the formula, you can solve this question very easily. Okay. Last 5 seconds. So what we have to calculate? The frequency deviation. Okay, and what is the frequency deviation? Frequency deviation will be the new frequency minus the initial frequency. Okay, so we have to calculate the new frequency first of all. So what is the formula in this case for calculating the new frequency? This will be Fn equals to Fi H into S minus del PD TD over H into S whole to the power 1 by 2. Okay. Now what is Fi? Initial frequency. This is 50. Inertia constant H, it is 4. S, it is 100. Okay. What is del PD? Del PD is the net load demand or load loss. Okay. So del PD, it will be positive if there is a load loss. it will be negative if there is a load loss, and it will be positive if there is a load demand. Okay, so what do we have here? Earlier we have 100 megawatt of load, and now the load is reduced to 70 megawatt. So how much is the loss in load? It will be 30 megawatt. Okay, and it will be negative because one line is tripping. Okay, so there will be a load loss. Okay, so we will take del PD to be minus 30 megawatt. So when you will put this value here, minus of 30 into TD. TD is how much? 0.5. Okay, TD is 0.5 upon 4 into 100 power 1 by 2. Now when you will solve it, what you will be getting? When you will solve it, you will be getting 50.92. New frequency will be 50.92 Hertz. Now, so what will be the deviation? Deviation will be Fn minus Fi. So 50.92 minus 50, that is 0.92 Hertz. This is what you will get, and which is given in option number C. Okay, so this is how you have to approach for this kind of question. Okay. So it is said that one of the transmission line is tripped. So if you have reduced one of the transmission line, if it is not there, obviously there will be a load loss. The output of the generator is reduced to 70 megawatt. So how much power we lost? Del PD will be 30 megawatt. Okay. If it is written like that, earlier we have written generator is reduced by 70 megawatt, that means the loss will be 70 megawatt. Right now we are only having 30 megawatt remaining. Okay. So just read the question carefully. What has been given here? Sir, from which concept Fn formula we derived? There will be a big derivation for this. Divya, don't go to that particular derivation. I will recommend you to just memorize this. Okay, I will just recommend you to memorize this. One more formula we have. If suppose B and R are given, so practice those formulas. Okay, if you will go into the derivation, it will take a long time, and that is of no use for us. So just be prepared with these particular formulas. Okay. In power system, we have to just practice few formulas. Okay, because if you will go into the derivation, it is going to take a lot of time, and which is highly not recommended. Okay. So now I hope this is clear to everyone. Okay. Moving towards the next question, just see this one. Two alternators rated for 160 megawatt and 120 megawatt respectively are connected in parallel to share a load of 250 megawatt. The larger unit has a governor droop of 5% and the smaller unit has a governor droop of 4% in the frequency from no load to full load. The load shared by smaller unit will be what, which we have to calculate. So out of these, which one will be the correct option? And we can take the no load frequency to be 50 Hertz. Okay. I hope you understood the question. So if both the generators with have respective droop of 5 and 4%, if they share a common load of 250 megawatt, what will be the participation of the smaller unit? Okay. So what will be the contribution of a smaller unit? This is what you have to calculate here, and your time starts now. And these types of questions, these are very, very important every year. Okay, from last 15 years, hardly there will be any year where gate authorities have not given a question like this. So these questions are very, very important question. Be prepared with these questions. Okay, every year they have given a question like this. Okay, I think last year we don't have any question, we didn't have any question from this topic. So this year it becomes even more important. Okay, so in last 15 years, around 10 times this question has come in gate exam. So this is a very important question. If you are prepared with these concepts, you are almost prepared with 2 marks. You can surely get 2 marks. So take your time and give me the correct answer. So last 10 seconds. Okay. So we have two generating units here. One is 160 megawatt, okay, and the other one is 120 megawatt. These are the two units, okay. What is the droop that the larger unit is having? It is having 5% droop, okay. And what is the droop that the lower unit is having? It is having 4% of droop, okay. And the no load frequency is 50 Hz. Droop means drop in frequency. So guys, if suppose you have 5% droop, so what will be the drop in frequency? 50 minus 5% of this no load frequency, okay. So it will be around 50 minus 2.5, okay. So how much it will be? 47.5 Hz will be the frequency at which this generator is operating when it is sharing this load 160 megawatt, okay. Similarly, with this generator, what will happen? It is having 4% droop, so 50 minus 4% of 50, okay. So which is around, I think, 2. So what will be the frequency at which it is operating? 48 Hz, okay. So 160 megawatt generator, when it is supplying 160 megawatt, at what frequency it is operating? It is operating at 47.5 Hz frequency. Generator 120 megawatt, when it is supplying this much of load, it is operating at 48 Hz frequency, okay. So this is their operating frequency when they are sharing exactly the same load. Now let us suppose that the contribution to this generator is PA and contribution to this generator is PB when they are operating at the same frequency. Let me call that frequency to be FN, okay. So when they are operating at the same frequency, the load shared by 160 megawatt is PA, load shared by 120 megawatt is PB. Now together they are sharing how much? PA plus PB. Together they are sharing 250 megawatt. Now what will be the value of PB? This is what we have to calculate, okay. So this is how you can decode these questions. Are you getting this? This is how you can decode this question. So from the given data, just see how we have decoded at what values what is happening here, okay. Now what we can do, just let me make a diagram of the situation we are in right now. So we are in this situation, just see. Let me call this to be the no load frequency 50 Hz. So this is my no load frequency 50 Hz. This is P in megawatt. So we have one generator which is supplying how much? If it is supplying 160 megawatt, okay. So if it is supplying 160 megawatt, at what frequency it is operating? Just see, it is operating at 47.5 Hz frequency. So this frequency is 47.5. Now we have another generator which is supplying 120 megawatt, okay. It is supplying 120 megawatt, and at what frequency it is operating? It is operating at a frequency of 48 Hz, okay. Now when they will be operating in parallel operation means they are operating at a common frequency. We are saying that the contribution of this generator is PA and the contribution of this generator is PB. Okay, this was having 5% droop, this was having 4% droop. So if they are operating at this common frequency, because when they are operating in parallel, frequency has to be the same. So when they are operating at a common frequency, the contribution of 160 megawatt generator is PA, 120 megawatt generator is PB. So we need to calculate the value of PB. Okay, so from this analysis to forming this particular figure, I hope everything is clear to you. Now these angles will be theta 1, these angles will be theta 2. Now we will calculate tan theta 1 here from the bigger triangle. So tan theta 1 will be what? It will be 50 minus, it will be from the bigger triangle, it will be 50 minus 47.5 divided by 160, or this is also equals to 50 minus Fn from the lower triangle divided by P of A. Let me call this equation number 1. Okay. Similarly, at this side, if we calculate tan theta 2 from the bigger triangle, then it will be 50 minus 48 divided by how much? 120. And from the lower triangle, we will get 50 minus Fn divided by PB. Okay, let me call this equation number 2. And we have one more equation, which is PA plus PB. Combinedly, it has to be 250 megawatt. Let me call this equation number 3. Now when you will solve these equations, okay, which are very easy, on solving these equations you might be getting the value of PB coming to be 121.43, which I am having 121.43 megawatt. Just see. So this is how we have solved this question. Now PB 121.43. So the closest answer is answer A. So this might be correct. Okay. Now these are very important questions. Every year, hardly there will be some years in which gate authorities, they haven't given a question from this topic. Last year was the case. So this year this big question becomes even more important for you guys. How to approach. Okay. Just be prepared with these kind of questions. You will surely get a question like this consisting of 2 marks. So from the given data, how you can get at what frequencies the both generators are operating. Okay. And then when they are operating in parallel, the frequency will be same. What is the contribution? This is what we have to determine. Now same situation we have plotted in this figure. Now in this figure you have to calculate tan theta 1 from upper and bigger and smaller triangle, tan theta 2 from bigger and smaller triangle, and you have to solve this equation. You will surely get your answer. Okay. So this is how you can approach for this question. And solve these questions as many times as you can, because they are the most probable question that you can see in the upcoming gate exam. Definitely it will be there. Okay. So now in these questions, the droop was given and at what frequencies the generator was operating, that we have calculated. Now you may have another situation. If this is not the question, then this will be the question in the exam. So see the next question. What has been given here is, there are 2 generators in a power system. No load frequencies of the generators are 51 Hz and 50.8 Hz respectively, and both are having droop constant of 0.86 Hz per megawatt. Total load in the system is 3 megawatt. Assuming that the generators are operating under their respective droop characteristic, the frequencies of the power system in Hz will be. So in last question we calculated what is the frequency at the 2 generators are operating as per their droop. Now those frequencies are given to you right now here. Okay. And then you have to solve this question. Okay. So let me give you time and let me see whether you are able to solve this as well. You may get these 2 types of question in the gate exam, and I am very sure about it. Either the droop will be given and you have to calculate no load frequency, then you have to proceed, or the no load frequencies are given directly, then you have to proceed. So in this way these type of questions may be asked. Take your time and think about it. You can solve it. Okay. So these two are the very important question. Either of them or the same type of questions will be the part of the upcoming GATE exam. Last 5 seconds. Okay, so see what we have to do here. If again I will try to make the same figure, so this is my P in megawatt and this is the frequency in hertz. So two generators are there. No load frequencies of the generators are 51 and 50.8 hertz. Okay, so this is generator 1 which is operating at a frequency of what? 51 hertz. So this frequency is 51 hertz. Another generator we have which is operating at a frequency of 50.8 hertz. So just see, this is the difference. Right now we are directly being given with the no load frequencies. Okay, so no load frequencies are given to us. Now having a droop constant of 0.86 hertz per megawatt. What is given? What is this data? Hertz per megawatt, F by P. Okay, isn't it that tan theta? When you will calculate tan theta, you will get the same thing. And total load in the system is 3 megawatts. So if this generator is sharing a load of P of A, and if this generator is sharing a load of P of B, okay, operating at the in parallel and at same frequency, then you know that it is given that PA plus PB, this is equals to how much? PA plus PB, this has to be equals to 3 megawatt. This is equation number 1. Fine. Now what we have to do here and what we generally do here, this is Fn. Okay, so let me call this angle to be theta 1 and let me call this angle to be theta 2. So what will be the value of tan theta 1? So the value of tan theta 1 here will be how much? 51 minus Fn divided by P of A. Okay, so this is frequency and this is megawatt. Frequency upon megawatt, hertz upon megawatt. This is what is given to us. Okay, 0.86. Let me call this to be equation number 2. Similarly, if we apply tan theta 2 in the other way, so what you will get? You will get 50.8 minus Fn divided by Pb, and Pb will be 3 minus Pa. Okay, this is what you can replace it with, and this is equals to again 0.86. Let me call this to be equation number 3. Now from equation 2 and equation 3, if you see, when you will solve this equation and when you will equate them, what you will be getting? When you will solve equation 2 and 3, so from 2 and 3, okay, when you will solve from 2 and 3, you will get the value of Fn. Okay, so when you will solve from 2 and 3, you will get the value of Fn, and that Fn, which answer, the answer that I am having is 49.51. Fn coming is 49.51 hertz. So just see, this is how you can solve these kind of questions. So this is the other way of asking these questions. Earlier the no load frequencies we have calculated, their individual power rating were given, what load they will share, this is what we have to calculate. Here no load frequencies are given, their individual ratings are not given. When they are operating in parallel, what will be the frequency, this is what we have to calculate. Okay, so this is the second way of doing this question. These are the two types in which this question may be asked, either in the first way or in this way. Okay, so just see, when you will solve this question, you will get the answer. So if this is given droop constant means you have to calculate tan theta 1. Okay, so in this way you can solve this question. I hope this is clear to everyone. So these are the two varieties of question. This is the first one and this is the second one. Be prepared with these questions. Definitely they will be the part of the GATE exam. Okay, I hope you understood. Now moving towards the next question. This is the question. Now long back these types of questions were asked in the GATE exam, and this time what I am thinking that they will definitely touch the travelling wave concept as well. Okay, and they will pick a question and give it in the exam 2024 exam. Okay, so be prepared with these two questions that we are going to solve in few minutes. So what has been given in this question is a 132 kV transmission line has an inductance and capacitance 0.1 millihenry and 0.02 microfarad per phase. The surge impedance loading in megawatt after placing 20% capacitance compensation will be. So without compensation and with compensation, when we have used 20% shunt capacitive compensation, what will be the new surge impedance loading? This is what we have to calculate. Okay, so just see, let me see whether you are able to solve this kind of questions, and your time starts now. So last 10 seconds we are having. Divya is saying B, 269.92. Yes, that's correct. Very good, Divya. Well done. So just see guys, without compensation. So if we see without compensation, what are the values that we are having? So if we call surge impedance to be ZS1, this is equals to under root L by C. So under root L, what is L? 0.1 millihenry. And C, what is C? It is 0.02 microfarad. Okay. So when you will solve it, you will get 70.71 ohm as the value of surge impedance. Okay. Then if I calculate surge impedance loading without compensation, so this will be equals to Vs square upon Zs1. So how much is Vs square? 132 kV. 132 square divided by Zs1, which is 70.71. kV square will be megawatt. So answer that we will be getting is in megawatt, and we are getting 246.4. 246.4 megawatt. Okay, so this is without compensation we are getting. Now what will happen with compensation? So if we talk about with compensation, okay, so with compensation, the new SIL, it will be equals to the old SIL under root 1 plus KCSH upon 1 minus KLSH and 1 minus KCSE. This is the formula that you have to use. Okay, this is the formula that you have to use here. Now what is KCSH? Percentage of shunt capacitance provided. KLSH, percentage of shunt reactor provided. KCSE, percentage of series reactance provided, series capacitance provided. Okay, in our case we are not given with this data, so just don't use them. We have been given that we are providing 20% shunt capacitance, so it will be 20% or 0.2. Okay, so now just see what is SIL1. It is 246.4 under root 1 plus 0.2 only, because these values we will not be using. Now when you will solve it, you will get 269.92 megawatt. Okay, so what you have to do, if you have a better practice of this formula, you will only require few seconds to solve this problem. Okay, and this year what I am expecting, that gate authorities, they will definitely touch travelling waves and they will give one question. Sir, isn't KLSH comes on numerator? I think this is correct, na Divya? And by the way, we don't require KLSH here. Okay, so that is not going to affect the answer. So what you can do, you can just cross check the formula used. Okay, I think this is the formula, but you can once cross check the formula. Okay Divya, is it fine? Since we don't require KLSH here, it is not going to affect this particular question. Okay, and this year my personal guess is that you may get a question related to this particular topic. They may give you all type of values and then they may ask you question. Okay, so be prepared guys. Okay, so now just see this question. Again, this is from compensation and it is also very important. A shunt capacitor of 50 MVAR is operated at 70% of rated voltage and 50% of rated frequency. The MVAR delivered by it will be. Okay, let me see whether you are able to solve this. We have the value of shunt capacitor and it is operating at 70% of rated voltage and 50% of rated frequency. Okay, and guys, in this part, Divya, you are absolutely correct. Okay, so this part will also come in the numerator, but we don't need this part here, so it is not going to affect anything. Okay, but this will also come in the numerator. So just make one simple correction, 1 minus KLSH. Okay, is it fine Divya? I think you were right, this will come in the numerator as well. Okay, but we are not using this part, so it is of no concern. Now focus on this numerical. This is a very good question and this is one of my favorite. Okay, So whether you are aware of compensation technique or not, if you have gone through that particular chapter or not, or topic, they will get to know. If you will, they will place a question like this. So this is one of my favorite, and you will see this particular question in the upcoming exam. Yes, absolutely correct, Divya. 12.25, very good. This is the correct answer. Okay. So just see, if we have shunt capacitive compensation, so if shunt capacitive compensation we are having, in that case, you know that QC is proportional to V square into F. Okay, QC is simply proportional to V square into F. If suppose we have shunt inductive compensation, okay, if suppose we have shunt inductive compensation, in that case QC is proportional to V square by F. Okay, the compensation power required is proportional to V square into F in capacitive compensation. In shunt inductive compensation, it is proportional to V square by F. Okay, so this small thing you have to remember. Now what has been given to us? Shunt capacitor. Okay, so we have shunt capacitor here. So what will be QC2, or simply if I write Q2 upon Q1. So from this particular data, just see shunt capacitor. So it will be simply V2 upon V1 square into F2 upon F1, isn't it? So now what will be Q2? So Q2 will be Q1. Q1 is how much? 50 MVAR. And what is the change in voltage? 70%. So 0.7, and change in frequency 50%, 0.5. So what you will be getting after putting the values? What you will be getting here? 12.25. This is the answer that you are getting, 12.25. So option C will be the right option. Is that fine? Tell me, just cross check, solve once again. Divya, your answer is absolutely correct. Let me verify it. Oh yes, a square is also there. I think then you will be getting the same answer. Okay. So is it fine? 12.25 is the correct answer here. Okay. I am also getting the same answer. So this is how you have to approach for this question. Now what they can do, they can either ask you a question in the same format, or they can replace with this question with inductor, or they can give you both the ways. They can give you with the capacitance, and they can ask you with the inductance. Okay, for inductance. So if you know this simple trick, okay, you will be able to solve this question anyway. Whatever they want to ask, you will be able to calculate it. Okay, so be prepared for this kind of question. This is my favorite one. Okay, so let me move to the next question. Just see this one. Okay, this is also very, very important. 2 times gate authorities have asked this kind of question. Again this may come. Okay, so that's why have a practice of this kind of question as well. A 3-phase 50 Hz 440 kV transmission line is 400 km long. The line inductance is 1 millihenry per kilometer per phase, and the capacitance is 0.01 microfarad per kilometer per phase. The line is under open circuit condition at the receiving end and energized with 440 kV at sending end. The receiving end voltage in kV will be what? So we have to calculate what will be the value of VR if it is operating under no load with given data. Okay, so your time starts now. Take your time and solve this question. Okay, these 3 questions these two questions, okay, this one and the compensation question that I have taken are from traveling wave, and this year you will definitely get a question from traveling wave. You can expect a question, okay, and if it is a question from traveling wave, this is the these are the probable ones. So line is operating under no load, sending end voltage is given, and we have to find what will be the receiving end voltage, okay. So 1 minute is still there. I hope that you guys can solve this question. Come on guys, you can solve this question. Last 10 seconds. Any answer? Okay. So under no load. Okay, what do we have under no load? Under no load means we have IR equals to 0, and in that case VR will be equals to VS upon A. Now Vs value is given to us. Vs value is basically 440 kV. We don't have the value of A. How to calculate A? A is basically what? 1 plus Y into Z by 2. Now what is this Y and Z? Admittance and impedance. Okay. So what is admittance and what is impedance? So impedance is R plus J omega L, and admittance is G plus J omega C. Now they have given that the line is lossless. So if the line is lossless, that means R and G both will be taken 0. So R and G both will be 0. So what will be the value of Y into Z? So Y into Z that we will be getting is equals to what? Y into Z will be equals to what? Tell me guys. It will be, or just see what we can do. We can calculate gamma. Gamma is basically under root of YZ, okay, and this is also equals to alpha plus J beta. So if the line is lossless, there will not be any alpha and we will only be having beta, and beta is equals to omega under root LC, okay, which is under root of YZ. So beta is basically equals to omega under root LC. So this we can also write to be 1 minus beta square by 2. When you will put the value of Y and Z by assuming G and R to be 0, you will get 1 minus beta square by 2, and beta is omega under root LC. Okay, beta is omega under root LC. So we have been given with the omega and LC value, so we can calculate beta in that way, or what you can do is you can calculate beta in this way as well. Beta is 2 pi FL upon V. Okay, this is the modified form of this equation. Omega you can write 2 pi F, and length we have taken because L and C are given in per kilometer. Okay, so when you will modify this formula, this is what you will get, and then we can write 2 pi FL upon V will be 1 upon under root LC. Okay, the speed of light, this is what we have to calculate here. Okay, so what we can do, we can calculate this separately. So V 1 upon under root L into C. Now what is the value of L and C? Just see here, L is given 1 millihenry and capacitance is 0.01. Okay, so just put the value 1 millihenry and 0.01 microfarad. Okay, both are given in per kilometer value. So when you will put into L here, so convert them into from per kilometer values to Henry in microfarad, then L will come into the numerator. This is what we have done here. So now when you will solve this, it will come 3.16 into 10 to the power 5 kilometer per second. Okay, length we are taking in kilometer. Now come back here. 2 pi f, 2 into 3.14 into frequency is 50, and what is the length given to us? 400 kilometers. 400 kilometers divided by v is 3.16 into 10 to the power 5. Now when you will solve it for beta, the beta value coming is 0.398. Okay, the beta value coming is 0.398. Now what is a? 1 minus beta square by 2. So 1 minus 0.398 square by 2. So from here what will be the value of a? The a value that you will be getting is around 0.92. Okay, then we have to calculate the VR value, which will be equals to Vs over a. So Vs is, I think, 440 kV, yes, divided by 0.92. So how much we will be getting? We will be getting 478.76 kV. So under no load, receiving end voltage will be greater than the sending end voltage. Is it so? Yes. That means we have done correct. Okay, this is absolutely correct. So just see, approach is very much important. This is how you should approach for these kind of questions. 2 times they have been the part of GATE exam. Be ready for the next time as well. So whenever these kind of questions will appear, what you have to do? You have to calculate a, and a is 1 minus beta square by 2. Don't do this exercise next time. And beta is 2 pi fl upon v. V is the speed of light. So calculate the speed, put the values, get the beta, then a, and then you can calculate the receiving end voltage. This is how you have to approach for these kind of questions. So I hope this is clear to everyone. Okay, and this is very, very important. 2 times they have been the part of GATE exam. Be ready for the next time as well. Okay, so I hope you got it. Okay, I hope you got it. So this is all about the compensation technique. So guys, I hope you are liking this session. If you want to get more such experience, join our Telegram channel, where you will get information about upcoming webinar, seminar, daily quizzes will be there, and the PDF of each YouTube session will be provided to you as well. Now moving towards the next chapter, which is the load flow analysis. Okay, so in the load flow analysis, what are the important topics? You can get a question from classification of buses, which we already got in the year 2023. Bus admittance matrix. Every year there will be a question from bus admittance matrix. There will not be any single GATE exam where they have not asked a question related to bus admittance matrix. Jacobian matrix is also very, very important, and economic load dispatch. This is also one of the one topic which has its present on all of the recent GATE exams. Okay, so these are the very important topic: bus admittance matrix, economic load dispatch. So let's get started with the very first question from load flow analysis, and this is the question. The 4 bus system is given below. So we have a 4 bus system. Let me number them: 1, 2, 3, and this is the 4th. All values are marked in ohm. Then we have to calculate the value of y11 minus y14 plus y23 plus y34. So what will be the value of these? This is what we have to calculate here. Okay, and across every bus, if you see, the values are same, the elements connected are same. Shunt element is 0.2, and impedance value between the buses is 0.5. So you can number them in any order. Either you can name them 1, 2, 3, 4 in this order, or 1, 2, 3, 4 in this order. Everything is fine. Now you have to calculate the value of these. Okay, so for this you need to calculate all these admittances. Okay, and your time starts now. And I am giving you 3 minutes for this question. Okay, because it requires time. Very good. Very good. So C is the correct answer. Okay. Now let's see those who are not able to solve how they can proceed for that. So what do we need? We need the value of y11. How to calculate y11? So y11 will be sum of all admittance connected to bus number 1. Now just see, everything is given in ohms. That means we have been given with the values of impedance, not the admittance. So we need to convert them into admittance. Okay. So y11 means all the elements connected into bus number 1. So in order to calculate that, these are the impedance. You have to convert them into admittance. So you will have to do the inverse of impedance. Okay. So these elements are connected to bus number 1. Just do the inverse of them, and then finally what you will be getting? You will be getting minus of J10, minus of J2, minus of J2. Okay. So what will be the value of y11? Y11 will be coming minus of J9. Okay. Then we require the value of y14. So what will be the value of y14? Y14. So element connected between 1 and 4 is 0.5. So 1 upon J 0.5, and what you will get? You will get minus J2. Then we require the value of y23, and what will be y23? Element connected between 2 and 3. Again this is the same, 1 upon J 0.5. So you will get minus J2. Then we require the value of y34, element connected between 3, 4. Again it is the same, 1 upon J 0.5. So you will get minus J2. Now when you will sum them up, y11 minus of y14 plus of y23 plus of y34. So how much they will give you? Just see, y11 is minus of J9 minus y14 is minus of J2 plus y23 is minus of J2 and y34 is minus of J2. So how much this will be? This is plus J2 minus J2 get cancelled, minus J9 and minus of J2. Anywhere that anything wrong that we have put here? Yes, one thing that we have mistaken here, just see here, y14, y23 and y34, okay, they are the diagonal element, isn't off diagonal element, and for off diagonal element we have to put a minus sign here as well. Okay, so when you will put a minus sign, everything will become plus. So in off diagonal element there will be a plus sign coming here. Okay, so now what you will be getting? You will be getting minus of J7. So ultimately the answer will be 7, which is C. And Divya, your answer is absolutely correct. Yes, diagonal elements are positive, and in Y bus matrix all the off diagonal elements are negative. Okay, so you have to take care of this extra sign here. Now you can do two mistakes here. Okay, so intentionally I did that mistake, that I didn't put a minus sign here. This is the one mistake that you can do. Other mistake that you can do, that instead of, if suppose you miss this line that the values are given in ohms, and if you are not inversing them, okay, if you will do with impedance directly, that is wrong. Okay, so always make sure that the whatever is given to you is in ohms or is in Siemens, means it is impedance or it is admittance. One thing. Second thing, diagonal elements are positive, okay, and off diagonal elements there will be a negative sign before them as well. Okay, so these two are the mistakes that people can do in these kind of question. Otherwise this seems to be a very easy one. Okay, and everybody knows about how to calculate Y bus matrix and everything. So guys, this is a kind of question which can be asked in the GATE exam. They have asked everything related to Y bus, nothing is left. So in this way they can modify the question. Okay, so very good, you all have solved this correctly. Now moving towards the next question. Now if suppose there is a transformer in between two buses, this creates a lot of problem. Okay, so be prepared of these kind of questions as well. So what has been given to us is two buses 1 and 2 are connected with a transmission line, admittance Y. Just see, we have been given the admittance, so we don't need to convert impedance into admittance. at bus 1 end there is an ideal transformer with turns ratio 1:A. The bus admittance matrix for this particular system will be what? So we have to calculate what will be the bus admittance matrix for this kind of system. Okay, so let me solve this first. So this is the system and we have to calculate the Y bus matrix for this. This is the voltage V1. So we will be having a voltage V1 here. Let me call this voltage to be V1 dash. And if suppose this current is I1, then this current will be I1 dash. If this is V2, so we will be having an I2 current here. Okay. Now one thing that is sure here is that V1 upon V1 dash is 1 upon A. Okay. So what will be V1 dash? V1 dash will be A times V1. And the second thing that we have is that I1 upon I1 dash, it will be A upon 1. So what will be I1 dash? It will be I1 upon A. This will be second equation. Okay, so this is what we can directly refer from this diagram. Now after that, if you see I1, if suppose I have to calculate I1 dash current, how I will be calculating this? This will be V1 dash minus V2 into Y. Okay, you know that I is equals to V upon Z and 1 upon Z is Y. So this is how we have written this equation. Now just put the values. I1 dash is I1 upon A. V1 dash is how much? V1 dash is A V1 minus V2 into Y. So what will be I1? I1 will be A square Y into V1 minus A V2 AY into V2. Okay, so this is our first equation. This is what we have got as I1 value. Now you also know that I2 dash is nothing but minus of I1 dash. Yes or no? I2, sorry, not I2 dash. I2 is nothing but it is I1 dash. Okay, and what is I1 dash? It is minus of I1 dash. So I1 dash is what is I1 dash? I1 upon A. Okay, from this transformation that we obtained. Now if we put the value of I1, what we have obtained as the value of I1, A square Y V1 minus AY V2. Okay, so what you will get? You will get minus of AY V1 plus of Y V2. This will be the value of I2 and this is my equation 2. Now if I write equation 1 and 2 in matrix format, I1 and I2, they will be equal to what? We have A square Y and we have minus of AY. Then we have minus of AY and then we simply have Y. Okay, so just see Y12 and Y21, they are same? Yes, they are same. That means absolutely correct. V1 and V2. So this will be your Y bus matrix. A square Y and Y, they are diagonal element. Minus AY and minus AY, they are off diagonal element. So this is how you can solve this question. So which option is correct? A square Y and Y minus AY and minus AY means this is given in option number B. Okay, now you can prepare yourself with this particular case. Whenever you have a transformer connected between any of the two buses, how to write the Y bus matrix directly, and the transformation ratio is 1:A. So this element will be A square Y, this element will be Y, and this element will be minus AY minus AY. You have to practice to write this particular Y bus matrix. Okay, because this can save your lot of time. I hope this is clear to everyone. Okay, so this is how we can solve this question. Okay, now moving towards the next question, an application of the concept that we learned. For a 3-bus system shown below, the voltage ratio of regulating transformer is 0.5 per unit. So the voltage ratio of the regulating transformer is how much? It is 0.5. Okay. Then the value of Y11 element of Y bus matrix will be what? Okay, so just see. 1:A is or if I write the transformation ratio 1:A, okay. So the voltage ratio is 0.5. So 1:A is 0.5. That means what will be the value of A? The value of A will be 2, isn't it? Yes, yes, Divya, you are absolutely correct. Okay. So the value of A will be 2 here. Fine. Now, what is, now just see the case we have obtained. We have two buses, bus number 1 and bus number 2, and in between these buses we have an element and there is an transformer connected. And can you see, ohm inverse is written, means the values are already in admittance form. Okay, so we don't have to convert impedance into admittance, they are already given in admittance form. So this is the first thing that you will look for. Then you can see we have bus 1 and bus 2 in which an element is connected with the transformer with some ratio. So this is the case that we discussed, isn't it? Now if you have this particular case, what we have seen, what will be our Y bus matrix? So our Y bus matrix will be like this. Okay, just see, it will be A square Y minus of AY minus of AY and then Y. Okay, so from here what will be the Y11 element? A square Y. What will be the Y22 element? It is Y. And what will be Y12 element? Y12 element is actually minus of Y12. So minus of AY, that is AY. Okay, isn't it? Off diagonal elements are negative. Okay, so this is how you will get this value. I hope this is clear to everyone. Okay, I hope this is clear to everyone. Now just see what has been given to us. So we have bus 1 and bus 2. I am just simplifying the things for you. So bus 1 and bus 2 we are having. This is like the way we have. Now for this Y bus matrix we have already written. Okay. Now Y12 and Y12, Y21 means the element connected between the buses. So element connected between the buses is having a value of AY. Just see here. Okay. Now Y11 is not only AY, it is different. So what will be the value of Y11? So it is the value of element connected at this bus. Okay. So Y11 and Y22, they are not AY, that means there are something else connected to them. So how you will calculate this value and this value? These are the values of shunt element connected. So in order to get the shunt element, you have to sum up the rows, isn't it? And you will get the value of shunt element connected. So if you will sum up this row, A square Y minus AY. So what you will get? A minus 1 Y. Or is it correct? A square Y, what we will get? A minus 1 Y. Yes, now this is correct. Similarly, if you will sum this up, what you will get? You will get 1 minus A into Y. So these will be the element connected to shunt element connected to these buses. Is that clear? Is that understood? Okay. So if suppose there is a transformer in between two buses, this is the Y bus matrix. From the Y bus matrix, if I just try to draw diagram of it in terms of elements, okay. So Y11 element, diagonal element will be A square Y, Y22 will be Y. And off diagonal element, it will be AY. Off diagonal element means the element connected between the buses, and since this element is not equal to Y11, means we are having something else as shunt element. So this shunt element will be what? When you will sum up this row, you will get this shunt element. When you will sum up this row, you will get the shunt element connected to bus number 2. Okay. So just see, this is what we will get. Okay. So now this particular line will be replaced by this circuit. Okay. So if we do exactly the same, just see what we will be getting. So this line will be replaced with a line only having a Y value. And here we will be having a shunt element of value A minus 1 Y. And here we will be having a shunt element of value 1 minus A into Y. Just see. This is how you will replace this line. Okay. Sir, shunt capacitor and shunt capacitor and line capacitor both are different. Yes, they are different, Divya. Where we are mixing them? We are not mixing them, isn't it? Shunt capacitor and line capacitor, they are different thing, isn't it? So this element that we have, okay, this is the line element, and this element will be a shunt element. How we come to know that there is a shunt element present? Because y12 and y11 are different values. If y12 and y11 are same values, then it is guaranteed that we don't have any shunt element, isn't it? Or other way, if you sum up the row and you are getting 0, that means there is no shunt element connected. Now whether these shunt elements are inductor or capacitor, right now we are not able to comment, okay, because we don't have their values. When you calculate the value, then you will be able to realize, okay. So just see, if we have this line, we will replace this with this one. This is what we have done here, okay. Now you can have a better practice of replacing them. If you can practice them replacing them directly, you will save a lot of time of yours, okay. So now this is what we have done, and what we have to calculate, we have to calculate y11. So this is bus number 1. For y11, we only need the elements connected to bus number 1. So bus number 1 has this element, okay, which is minus J1. Bus number 1 has this green element, which is A minus 1 into Y, and bus number 1 has this green element, which is A into Y. Okay, now it is the time to put all the values. A value is 2, and what was the value of Y? Minus of J1. Okay, and A value is 2 minus of J1. So what we will be getting as a final answer? It will minus of J1, 2 into 2 minus 1, it will give you J2, and this will give you minus J2 back. So is it minus J5? Okay, minus J5 is what we are getting here as Y11. Okay, so Y11 element will be what? In magnitude form it will be 5. This is what you have to write here. See, this is how you can apply this concept, okay, and you can solve this question. So this was the concept, okay. So you have to practice how to write the Y bus matrix for it, okay. Then from this Y bus matrix, if we realize its network, this is a kind of situation we are in. So whenever we will get in between two buses, we have a transformer and an element, we will replace this combination with this combination, and when we will do that, we will get something like this. Now whatever element, or if suppose we want to calculate the complete Y bus matrix, everything possible for us, okay. So this is how we have reduced the task and we got this answer, okay. I hope you got the message, what exactly you have to practice here. Fine. Now if you have understood this, then can you solve this question having the same application? The one line diagram of a 4 bus power system is shown below. The reactants are given in per unit. A common MVA base is taken. Transformer has a tap setting of 0.8 to 1. Normally what we used to write is 1:A. Okay. So 1 by A is given to us 0.8 upon 1. So from here what will be the value of A? 1 upon 0.8 or 1.25. Is that correct? Is that correct, guys? Just tell me. Okay, so this is how you can calculate A. Now what you have to do is, the element Y22 of the bus will be what? You have to calculate the element Y22 of the bus. Okay, so this is the transformer and this is the impedance of the line given. Now everything is given in terms of impedance here. Okay, everything is given in terms of impedance. There is no mention that you have to take admittance. These are admittance. Okay, so everything is in impedance. So your time starts now. Whatever you have learned in the last question, you have to exactly apply the same concept here, and this problem will be done. Let me see, are you able to do this? Come on guys, you can solve this question. Okay, you have to replace this line with the equivalent one. you have to replace the line with the equivalent one. Okay. Come on guys, you can solve this question. Okay, what you learned in the last question you have to apply exactly the same here, and everything is given in terms of impedance. Okay, last 4 seconds. Any answers? So see what we will be doing here. If I redraw this, so this is what we are having. Okay, or let me redraw it with admittance. So these parallel combinations I can do, and I can draw one line here only. So see, this is 1, 2, 3 and 4. Okay, so what we will get here, it is parallel combination of j.4 and j.1. Okay, so what it will be, parallel combination of j.4 and j.1, 0.4 into 0.1 divided by 0.5. How much we are getting? Can anybody tell me? .08. Okay, so this will be 0.08. And what do we have here? We decided that the value of A is 1.25, and what is the admittance given? Impedance J 0.025. Okay, and what is this? J.5. Okay, now you just tell me when you will replace this. Okay, so when you will replace this, what will be the value here? You will be getting something called as AY. Okay, and then you will be getting an element here which has the value of A minus 1 into Y, and then we will be having an element here which is having a value of 1 minus A into Y. Okay, bus number 1, bus number 2, this is the equivalent one of it. Then we have bus number 3, then we have bus number 4. So everything else will be like this. We have to calculate the value of, this is J.8. Okay, we have to calculate the value of Y22. So Y22 will be A times Y. Okay, all the elements connected to bus number 2 will be added. So AY plus 1 minus A times Y plus J.8. Okay, or 1 upon J.8, because it is in impedance format. Okay, so now put the values here. A is 1.25. Okay, and what will be the value of Y here? If Z is this, so Y will be what? 1 upon J, 0.025. Similarly, what we will get here? 1 minus 1.25 and again y will be 1 upon j 0.025, then 1 upon j 0.1. So this will be how much? Minus of j, and we will get 1.25. Okay, so now you only have to do, you have to solve this equation, and the answer that I am having is minus j 52.5. Just verify whether this is correct. Okay, just verify whether this is correct, or if you are getting any other answer, just post your answer in the comment box. Okay, so have you seen what we have done? If you are very well prepared of this particular thing, that if we have a transformer, how to replace that transformer, then there is nothing left here, isn't it? So we replace this transformer with this equivalent. Okay, and then y22 if you have to calculate, you will be taking this element and this element, and everything has to be in admittance format. So ay plus 1 minus ay plus 1 upon j.8, because impedance was given. Okay, now what will be y? Y will be 1 upon this impedance. Okay, so just see, after putting all the values you will get this answer. Just verify whether this answer is correct and post your answers in the comment box. Okay, so just see, this is how you are able to solve these kind of question. Okay, now everything else has been asked from Y-bus metric. There are very less chances of any other questions coming from Y-bus, but this has a huge probability, because this kind of questions were rarely the part of the GATE exam. So they may ask a question related to a transformer connected between two buses. Okay, so we did 3 questions related to these. I hope you got a better practice of them. Okay, now let me move to the next question. So the Y-bus matrix, bus admittance matrix, is given to us. The number of buses with shunt capacitance and shunt inductance are. How many buses will be having shunt inductance and capacitance? This is what you have to comment, and your time starts now. I think this is a very easy question for you. Okay, that's why I want answer from you all. So try to solve this question. You can do this. Okay, last 3 questions that we discussed, buses having transformer, is very important. Prepare this question, and they can be the part of this upcoming GATE exam. Okay, Y-bus is a very important topic. Every year we had a question from this particular topic. So GATE authorities, they are not left with so many chances from Y-bus, so that they can prepare a new question. So there are huge probability that these kind of questions may be the part of GATE exam. Come on guys, it will not take that much time. It's very easy one. Last 15 seconds. Okay, any answers? Divya is saying A and D. Okay, let's see. So bus admittance matrix of power system is given, and we have to comment about the shunt element. So if we want to do that, we have to sum up the rows. So if we just sum up the first row, what we will get? Minus J40 plus J5 plus J10. Okay, so this will be what? This will be minus of J25. Okay, minus of J25. This is what you will get when you will sum up the first row. this is what you will get, minus of j 25. Fine. Now when you will sum up the row number 2, so if you will sum up row number 2, you will have j5 minus j20 plus j8, and how much you are getting? Minus of j7. When you will sum up the row number 3, you will get j10 plus j8 minus j15, or it will be plus j3. Okay, and everything that you have solved here is in terms of admittance, not in terms of impedance. Okay, so if it is an impedance, in terms of impedance, L, how it is represented? J omega L. C, how it is represented? Minus j upon omega C. So in terms of impedance, if j is positive, it is inductor. Okay, and in terms of admittance, how it will be represented? Minus j upon something. Okay, so you will get minus j, and here you will get plus j. In terms of admittances, you will just inverse the impedance and you will get this value. Okay, so minus j upon omega L, or you will get j omega C like this. Okay, so in terms of impedance, if it is L, j will be positive. In terms of admittance, with inductance, j will be negative. In terms of capacitance, with impedance, j will be negative. With admittance, j will be positive. Okay, so here you are getting negative j. That means this is what? This is an inductance. Okay, what is this? This is also an inductance, and this is positive, so this will be what? A capacitance. Isn't it? 2 inductance and 1 capacitance. Okay, so 2 inductance and 1 capacitance. So 2 buses with shunt inductance, this is not the only one. 1 bus with shunt inductance, 2 buses with shunt inductance, 1 bus with shunt capacitance. So 2 buses are there with shunt inductance and 1 bus is there with shunt capacitance. A and D are the absolutely correct answer. So Divya, your answer is absolutely correct. Well done. Okay, this is also a kind of question, okay, which gate authorities will definitely can give you. Okay, so I hope this is done with everyone. Now just see this question, and this is one of my favorite. In a load flow solution, if the voltage at bus I is Vi equals to 1.208 angle minus 17 degree per unit, and the voltage at bus J is Vj equals to 0.713 angle 12 degree, which of the following statement is correct? Power flows from I to J and Q flows from J to I. P and Q both flows from I to J, P flows from J to I, Q flows from I to J, and P and Q both flows from J to I. Okay, very interesting question. So let me see what answers you people think might be correct here. Divya is saying C. P flows from J to I, Q flows from I to J. Very good. I don't think we need a timer. So you are that much fast. Lightning speed. Very good. We have 2 buses, bus number I, bus number J. Okay, and they are connected with some element with each other. Okay, what is V and V of I? This is 1.208 angle minus 17 degree. What is V of J? This is 0.713 and angle is 12 degree. Okay, so just see. Regarding P and Q, we have to comment. So P is given by Vs into Vr, or we can write here Vi into Vj upon, let me call this element to be X, upon X sine of del 1 minus del 2. Okay, so if del 1 minus del 2 is greater than 0, if del 1 minus del 2 is greater than 0, then P flows from I to J. Okay, then P flows from I to J. And if del 1 minus del 2 it is less than 0, in that case P flows from J to I, because sign del 1 minus del 2 will be negative, power will be negative. So what condition we have here? Del 1 is minus 17, del 2 is 12. So we are having this condition. Okay, so power will flow from J to I. So we are having flow of P from J to I. Now what about Q? Okay, so what about Q? So if I write the expression for Q, so Q expression will be Vi Vj divided by x cos of del 1 minus del 2, okay, minus Vj square upon x. Del 1 minus del 2 is a small quantity here, okay, and with inside the cos plus minus does not matter. If we assume that cos del 1 minus del 2, okay, is very close to 1, because difference is close to 5, which is almost very close to 0. So if we assume that this is equals to 1, then what we will get? We will get here Vj upon x Vi minus Vj. Okay, this is what we will get as Q. Now if Q is positive, it is possible when Vi is greater than Vj. Okay, so just see, if we have Vi greater than Vj, this means Q is positive and it flows from I to J. If Vi is less than Vj, Q will be negative and it is flowing from Q to J, I. So that means how will be the flow of Q? The flow of Q will be from I to J, because Vi is greater than Vj. Okay, so P flows from J to I and Q flows from I to J. This is the correct answer. Okay, well done Divya, very good, very good. Okay guys, just see, this is what you have to see regarding the power flow. Regarding the flow of P, you have to see del 1 minus del 2. Regarding the flow of Q, you have to see about the voltages, which voltage is greater. That clear to everyone? Okay, now moving towards the next question, just see this one. So the reactance diagram of a power system is shown in the figure. All impedances are marked in per unit, all the values are impedance. Okay, the magnitude of sum of all diagonal elements. So how many buses we have? 1, 2, 3, 4. So we have to calculate the magnitude of sum of all diagonal elements. Okay, we have to calculate this and your time starts now. This is the impedance diagram of the bus which is given to you. All the values are in impedance. Be very clear with that. Okay, come on guys, you can solve this type of question. I'm sure about it. Even it will not take 2 minutes to you. You can solve this question within a minute. Only 1 minute is left. Come on everyone, you can solve this question. It's not a difficult one. Last 5 seconds. So we have to calculate all the diagonal elements, and all the values are given in terms of impedance, not in terms of admittance. Okay. So voltage source are there, you can convert them into current source, but it is not going to affect the impedance value. So don't do that. Okay. So what we can do here, we need the value of y11. So what will be y11? Reciprocal of all the impedances connected to bus number 1, J5, J.2, J.2. So 1 by J5 plus 1 by J.2 plus 1 by J.2. How much we will get? Okay, Divya has got an answer 50.6, which is absolutely correct, Divya. Very good. So what you will get? You will get minus J10.2. Okay, then how much will be Y22? Reciprocal of all the elements connected to bus number 2, again J5. Okay, this value will also be J.2 and J.2. So 1 upon J5 plus J.2 plus J.2. So again you will get minus J10.2, which is same. Then Y33, reciprocal of all elements connected to bus number 3, J5 and 3J2. So 1 upon J5 plus there are 3J2, J.2. Okay, so how much we will get? Minus J15.2. Okay, minus J15.2. Then Y44. So Y44, there are 3 elements connected, all are 0.2. So what will be Y44? 1 upon J.2, 1 upon J.2 and 1 upon J.2. So what we will get? We will get minus J15. Okay. Now just sum them up. So what will be the summation of them? Minus J10.2 minus J10.2 minus J15.2 and minus J15. Okay. So how much you will be getting? 15 and 15 is 30, 50.6, and it's a magnitude, so you will get 50.6, which is correct. Very good, Divya. Okay. You are in great touch of preparation with power system. So this is how we can solve this question. Now moving towards the next question. This is from economic load dispatch, and just read this problem with me. Fuel cost for a power plant with 3 generating units are G1, G2 and G3. These are given. With P1 is the real power in megawatt. Assuming all 3 generator units are working simultaneously all the time, minimum and maximum loads on each unit can be 100 and 500. So no unit can be loaded below 100 and no unit can be loaded above 500. If plants are operating on economic load dispatch to supply the total power demand of 900 megawatt, then the power generated by each unit will be what? This is what we have to calculate. Okay, and your time starts now. Very conceptual question. Maximum and minimum powers are 100 and 500 megawatts. Okay. And together all of them are sharing a total load of 900 megawatt. Okay, let me be aside. Now this is a question. Take your time and get me the right answer. I think you people are finding it a bit difficult. Okay, so let that P1 is minimum. Okay, so if P1 is minimum, that means P1 is 100 megawatt. So if P1 is 100 megawatt, what will be FC1? Okay, for generator 1 it will be 20 plus 0.5 into 100, or what you will get? You will get 70. Okay, 70 rupees per hour. That will be the cost. Similarly, if suppose P2 is minimum, so if P2 is minimum, that means P2 is having 100 megawatt. In that case, what will be the FC2? It will be 50 plus 0.6 into 100, that is 110. Okay, so if P1 is minimum or P2 is minimum, still what you can see is that if P1 and P2 are minimum, then FC1 and FC2, even then their cost, operating cost, is greater than FC3, isn't it? If we are taking P1 and P2 to be minimum, even then what is there? Cost of operation of generator 1 and generator 2 is still greater than generator 3. That means if you are giving more load to generator 1 and generator 2, they are overloaded, while we have a third generating unit which is underloaded. That means the maximum load is given to which generator? FC3. Okay, so maximum loading will be given to this. That means it is sure that P3 will share the maximum load, and how much it will be sharing? 500 megawatt. Okay, why we are not saying that P1 and P2 will be 500? Because FC1, FC2, when we are taking the minimum for them, even then their operating cost is more than FC3. That means if suppose there is an increased demand, we will load F3 first for economical operation. Okay, so that means F3 can be overloaded, can take more load, and let us suppose that F3 is maximum. So we got that P3 is 500. Okay, and together P1 plus P2 plus P3, this is 900. So if you will put the value, what we will get? If we will put these values, we will get V1 and P1 and P2, they will be equals to what? 400, because now we know that P3 is 500. So P1 plus P2, they will be equals to what? 400. This is my first equation. Okay, now since we are operating under economic load dispatch, so if I just write that operating cost of generator 1 and generator 2 are exactly equal. Okay, FC1 equals to FC2, economic load dispatch. Then what will happen? We have 20 plus 0.5 P1. This is equals to 50 plus 0.6 P2, or what I will get? 0.5 P1 minus 0.6 P2. This is equals to 30, equation number 2. So I have equation 1, I have equation 2. Okay, from equation 1 and equation 2, when you will solve it, you will get the value of P1 and P2. So P1 will be 255 and P2 will be 245 megawatt and P2 will be 155 megawatt. Okay, so just see, P1 245, P2 155 and P3 500, that is A is the correct answer. So this was a very easy question, isn't it? But you have the conceptual clarity to solve this question. It is not like other question in which directly we have to apply economic load dispatch. Okay, it is some kind of indirect questions. What is the purpose of economic load dispatch? So that all the generators are well utilized, isn't it? Now if you will load P1 and P2 to be maximum, and we have one generator P3 which is already operating at a low cost, not overloaded, where it can be loaded more, this is not an economic load operation. Okay, so you have to take care of the economic load here, and this is how you will get your answer. Okay, now moving towards the next question. See this one. So what is given here? In a system consisting of two generating plants, the incremental cost in rupees per megawatt hour with P1 and P2 in megawatts are dC1 by dP1, dC2 by dP2 are given. The system is operating on economic load dispatch with P1 and P2 equals to this much and Deber PL upon Deber P2 equals to 0.2. The penalty factor for plant 1 will be what? Okay. So, whenever we are given with the losses, then what is the economic load dispatch? The economic load dispatch then is L1 dC1 over dP1. This is equals to L2 dC2 over dP2. Okay. So, let us first calculate the value of L2. So, what will be the value of L2? It will be 1 upon penalty factor for this. It will be 1 upon Deber PL over Deber P2. So, 1 upon 1 minus 0.2. So, you will get 1.25. This will be the value of L2. Okay. Now, come back in this equation and put the values. So, L1 is what we need to calculate. dC1 upon dP1 is 0.15 and P1 we can take 100 plus 150. This is equals to L2 1.25 Deber C2 upon Deber P2, which is 0.25 P2. So, P2 I can put again 100 plus 175. Do you see any other unknown other than L2? No. So, sorry, L1. So, when you will solve this equation for L1, you will get an answer 1.51. So, just see. This simple hack you have to apply in this question and this will be solved. Okay. So, this is a problem related to losses. Okay. Economic load dispatch considering losses. I hope you got it. Okay. And this is also very important. From economic load dispatch, I have taken some extraordinary problems. If there will be a normal problem, you will be able to solve. I have taken some extraordinary problems so that you get a practice of some unorthodox question. If there will be an orthodox question, you will definitely be able to solve. Now, see this question. Okay. So, this is also very important. A power system has two generating plants and the power is dispatched economically with P1 150 megawatt and P2 270 megawatt, 275 megawatt. The loss coefficients are also given. In order to raise the total load on system by 1 megawatt will cost an additional rupees 180 per megawatt hour. What is given? Lambda. Lambda is 180 rupees per megawatt hour. Okay. The penalty factor for plant 1 and additional cost per hour to increase the output of plant 1 by 1 megawatt will be what? Okay. Let me give you some time for this question. So, you have to calculate the penalty factor for plant 1 and you also have to calculate how much will be the cost for plant 1 and your time starts now. Okay. Are you getting what you have to calculate? You have to calculate L1 and you have to calculate what will be the value of Deber C1 upon dP1. These two things you have to calculate here, which I think you will be able to do. So, last 30 seconds guys, you can solve this question. Okay. Now, what kind of questions you may get from economic load dispatch? Either it will be a very straight question, you have to apply ELD, it will be a question related to penalty factor, okay, or it will be a question related to the loss coefficient, or it might be a question what we have solved, which was the first question from economic load dispatch that we have taken, okay. So it might be a question on from these categories. So last 5 seconds, any answer that I am getting? No. Okay, so we have to find L1, okay, penalty factor. You know that penalty factor L1 will be equals to 1 minus Deber PL upon Deber P1, okay. This is how we can find it. Now, how to find Deber PL upon P1? So, PL, equation for loss is what? B11. Equation for loss will be what? B11 P1 square plus 2 B12 P1 P2 plus B22 P2 square, okay. So, this is the equation that we have. Now, if I will differentiate it with respect to P1, it will give us 2B1 P1 plus 2B12 P2 and it will be 0. Now, if I put the value B11 is 0.10 into 10 to the power minus 2 and P1 and P2 is given what we have to take 150 megawatt plus 2 B12 is 0.01 into 10 to the power minus 2 and P2 that we have to take is 275, okay. So, when you will solve this value you will be able to calculate, and this is coming 0.245, okay. This is coming 0.245. Now, if you are getting this value and you will come back here and when you will put this value 1 minus 0.245, how much will be the value of L1? L1 that you will be getting is around 1.32. So, you got your one answer 1.32, which is option number A. Now, you have to calculate what will be additional cost per hour to increase the output of plant 1 by 1 megawatt, okay. That is, you have to calculate what? You have to calculate DC1 upon DP1, incremental cost, okay. This is what you have to calculate. So, whether we have to consider the losses or we don't have to consider the losses, we have to consider the losses, isn't it? So, if you want to calculate this, you know that loss equation will be what? L1 dC1 upon dP1, this is equals to L2 dC2 by dP2. Ultimately, this is equals to what? Lambda, okay. So, this is equals to lambda. So, from here what will be dC1 upon dP1? Lambda upon L1. What is lambda? Lambda is given to us 180. 180 divided by L1. L1 is 1.32. So, when you will solve it, you will get 136.36 as answer, okay, which is given here, option number D. So, just see, we are very well prepared for so many things, but what they are giving is a very tiny thing, and since we know that we are very much familiar of certain kind of problem from economic load dispatch, we will miss this particular thing, and see, the gate authority may ask a question from you from this particular thing, okay. So, guys, whatever questions I have taken from economic load dispatch, if you will be able to practice this question, you are almost prepared for this topic. Any question, if it is coming from this topic in the gate exam, you will be able to get it through, okay. So, moving towards the last question of today, and this is from Jacobian matrix. So, a power system has 20 generators, G1 to G20, out of which G8 is the largest, okay. D12 is 0.01. Acha, I have written a wrong value here. Yes, it is 2 into minus 0.01. That's fine, Divya Rao, okay. But the answer that you will be getting is same, okay, because calculations are there with me and I have calculated this, which I think you also will be getting, okay. Now, focus on this question. So power system has 20 generators, out of which G8 is the largest and hence chosen as reference bus. Okay, there is an indication in this line. G3, G7, G11 are operating at their maximum reactive power limit. If the total number of buses are 20, then size of Jacobian matrix in Newton Raphson load flow study will be what? And your time starts now. Come on guys, you can solve this question. It is a very easy one. Okay, we have two formulas for calculation of Jacobian matrix and both leads to the same value. You can use any one of them. So last 1 minute, and I don't think it is going to take more than 1 minute. Okay, come on everyone, you can give me a right answer for this question. Last 10 seconds. Okay, so what is the size of Jacobian matrix? And first of all, read the question. So how many total number of buses are there? Total number of buses are 20, out of which G8 is the largest and taken as reference. So G8 will be the slack bus, isn't it? G8 will be the slack bus. Okay, G3, G7, G8, G3, G7 and G11, they are operating at their maximum reactive power limit. So their reactive power is specified. So if about something we know that their reactive power is this amount, that means it is a load bus, because for a load bus P and Q values are specified. So this is going to be what? This is going to be a PQ bus. Okay, so PQ bus, how many buses are there? 3 buses. Okay, so if I now ask you that how many PV buses are there? Okay, so PV buses, just see, total buses are 20, out of which 3 buses are PQ bus and 1 bus is slack bus. So total PV buses will be 16, isn't it? Now size of Jacobian matrix, size of Jacobian matrix. There are two ways you can calculate this. One is 2 PQ plus PV. So 2 into PQ are 3 and PV is 16. So you will get 22. Okay. The other formula is size of Jacobian matrix, size of J matrix. This is equals to what? 2n minus m minus 2 into 2n minus m minus 2. Okay. What is n? Total number of buses. What is m? Total PV buses. Okay. So just see, from here also if you will calculate, so 2 into total buses are 20. Okay, minus total number of PV buses we calculated are 16, minus 2. So 40 minus 18, it will be 22. So both the ways you can calculate, it is coming same. Yes, very good, Divya. Okay, so this is a question from Jacobian matrix. So today what we have discussed, one chapter which is compensation technique, the other chapter which is load flow analysis. Two such important chapters which will definitely give you questions around 4 to 6 marks in the upcoming GATE exam. This year power system going to have a weightage up to 12 or 13 marks, out of which these chapters will definitely constitute 4 to 6 marks. So these are very important, and whatever questions I have chosen here, these are fantastic questions. If you are very much clear with the idea and the approach and the formulas used in these questions, you are very well prepared for these two chapters. So guys, practice these questions as much time as you can. Okay, so this is the end of the session today.